Hello, my name is Andrew Snowden. I'm from the University of Michigan, and this is my talk for the AMS sectional meeting that was supposed to be held at Purdue earlier this month, but that was canceled due to coronavirus. I was supposed to speak in the session called Stability in Topology, Arithmetic, and Representation Theory, organized by Peter Patz, Andy Putman, and Jeremy Miller. So let me thank them for inviting me to speak. All right, so as you can see, this talk is going to be about two tales from equivariant commutative algebra. But before we get to them, we need some background. So let's suppose we have a commutative ring R and a group G acts on it by ring homomorphisms. So by equivariant commutative algebra, I mean studying this ring, taking into account the action of the group. And my particular interest in this topic comes from the field of representation stability, where there are a lot of important examples. So one is if you take the group to be the infinite symmetric group and let it act on the infinite variable polynomial ring just by commuting the variables around. And another example is if you take the infinite general linear group and let it act on, for instance, the symmetric algebra of a polynomial representation. These things are called twisted commutative algebras. And we'll see more about each of these two examples later in the talk. But for now, let me just point out that the rings in both of these examples are very infinite. They're not Noetherian. And so you're not going to be able to say anything about ideals in this ring or modules over this ring in general. But the whole point of representation stability is that if you take into account the equivariance, then these rings actually behave very nicely, and there are a lot of things that you can say. And this principle has been used by a bunch of people in the last 10 or 15 years to prove some interesting results on things like the geometry of tensors or Stillman's conjecture. So that's why we care. We're in a situation where we have this equivariance, and you can't say anything if you ignore it, so you have to take it into account. All right, so in commutative algebra, there's a bunch of basic concepts. We have things like the idea of a Noetherian ring or a prime ideal or the radical of an ideal. And we want to make analogs of these definitions in the equivariant setting. And there's a very mechanical way to do this that works in many cases. And the procedure is to first take the usual definition of whatever concept you're thinking about and write it down using only ideals. You're not allowed to use elements. And then all you do is you change the word ideal to G ideal, where G ideal means a G stable ideal. And now that's your definition in the equivariant setting. So let's look at this for prime ideals, which is one of the most important concepts in commutative algebra. So if you look in a commutative algebra book, the definition of a prime ideal will be in terms of elements, but it's easy to convert it into a definition which only uses ideals as follows. An ideal P is prime if and only if, whenever you have AB contained in P, you either have A contained in P or B contained in P, where A and B are ideals of your ring. All right, so now that we've phrased primality using only ideals, we can make our definition of an equivariant analog, equivariant setting, just by changing all our ideals to G ideals. So here's the definition. A G ideal P is called G prime if AB contained in P implies A contained in P, or B contained in P for G ideals A and B. All right, so now that we have the definition, we can examine it and try to cast it in an elemental form, which will be easier to work with, and it's not hard to do that. Here's how it works. P is G prime if and only if. Whenever you have F times sigma G contained in P for all sigma in your group, you either have F and P or G and P, where F and G are elements of the ring. All right, so it's immediate from the definition that a prime that is G stable is G prime. The converse isn't true, and so maybe that's the first thing that we should understand, and we'll see that by looking at an example. So here's perhaps the simplest example of a G prime. So we're going to look at the ring, which is just a two-variable polynomial ring in X and Y, and we're going to let the symmetric group S2 act on this ring just by transposing the variables. And the statement is that the ideal P generated by X times Y is G prime, and this ideal is not prime. All right, so let's explain why this is true. So let's suppose that we have f times sigma g in P for all sigma, and we'll assume that f is not in P. So the vanishing locus of this ideal P is the union of the two axes, the x-axis and the y-axis. And so f doesn't vanish identically on this union, and without loss of generality, let's just say it doesn't vanish identically on the x-axis. So our hypothesis is that f of xy times g of xy and f of xy times g of yx both vanish on the union of the axes. And in particular, they both vanish on the x-axis. And since f doesn't vanish identically on the x-axis, it follows that both gxy and gyx must vanish on the x-axis. And therefore, g vanishes on both axes, so it belongs to P. And that verifies the criterion. So this is a G prime. So it turns out that this example is kind of representative for what happens with finite groups in general. So suppose for the moment that our group is finite, then we can say the following. If you have a G prime, then it is the intersection of the G orbit of some ordinary prime ideal. And moreover, this construction gives you a bijection between the G primes of the ring and the G orbits of primes. And so in particular, this shows that every G prime is a radical, because prime ideals are radicals and intersection of radical ideals are radicals. And well, I kind of take this to mean that for finite groups, G primes are not very interesting. We can understand exactly what they are in full generality. They're always radical, which means there's not really much subtlety. You can see everything using geometry by standard methods. And all this also holds for if G were a finite dimensional algebraic group instead of a finite group. And since normally, when people, most people doing algebra, when they're working with a group, it's going to be some kind of finite group or a finite dimensional algebraic group. This concept is not so interesting, so I think that's why it hasn't been studied so much. As far as I know, equivariant commutative algebra, at least of the flavor I'm talking about, has not received much attention, and I think that's because it's not that interesting in settings that people are usually in. Okay, so now let's look at another example which shows that the concepts become more interesting in the settings that we care about in representation stability. So let's suppose that we're in this case where we have the infinite symmetric group acting on the infinite variable polynomial ring. Then we have the following proposition, which says that the ideal P that's generated by the squares of all the variables is G prime. And obviously this ideal is not a radical ideal, so it gives an example of more interesting behavior. So let's see why this is true. So again, let's suppose that we have f times sigma g contained in P for all sigma. And here's the key point. Since we're in infinite many variables and we have the infinite symmetric group acting, and f and g are polynomials that use finitely many variables, we can pick some element of the symmetric group sigma so that f and sigma g do not have any variable in common. Okay, and so we're given that f times sigma g belongs to P, and therefore every monomial in f times sigma g, when you write it out, has to have the square of a variable in it. That's exactly what it means for something to belong to P. And if you think about it for a minute, that says that the same has to be true for either f or sigma g, and therefore either f or g, which says that one of f or g has to belong to P. So that proves that it's G prime. Okay, so that's prime ideals in the equivariant context. Let's move on and do another definition. Let's think about radical ideals. So once again, the usual definition of radicals is in terms of elements, but it's easy enough to recast it using only ideals. So if you have an ideal A of your ring, the radical of A is the sum of all ideals C such that some power of C is contained in A. And so now we get our definition of G radical. So suppose that A is a G ideal. We define the G radical of A, and we're going to denote this by rad sub G of A, to be the sum of all G ideals C such that some power of C is contained in A. All right, so now that we have the definition, we can once again examine it and figure out an elemental version of it, and that's given by this proposition. An element x belongs to the G radical if and only if there exists some integer n such that any product of n elements in the G orbit of x belongs to A. All right, so in ordinary commutative algebra, there's a close connection between prime ideals and radicals, and the exact same relationship holds in the equivariant setting. If we have a G ideal A, then rad G of A is the intersection of all the G primes containing A. And basically the normal proof of this applies in the equivariant case with small changes. It's a good exercise. And finally, one more definition. We define the G spectrum of our ring R, which we denote spec sub G of R, to be the set of all G primes. And we equip it with the usual Zariski topology. And so by that, I mean, if you have an ideal I, you have V of I, which is the set of all primes containing I, and those are your closed subsets. And note that since, I should have said G primes that contain I, and since we're only looking at G primes, if we have a G prime that contains an ideal I, it's going to contain the G ideal that I generates. So when we define the topology, it doesn't make any difference if we use all ideals or just G ideals. We'll get the same closed sets. And by this relationship between G radicals and G primes that we saw in the previous slide, that implies that the closed subsets of the G spectrum are in one-to-one correspondence with the G radical ideals, just like in ordinary commutative algebra. And we can now formulate the main problem that we're interested in this talk, which is to describe the G spectrum in cases of interest. So for actions on rings that we care about in representation stability, we want to be able to figure out what are all the G primes. And the motivation for that is that just like in ordinary commutative algebra, that's going to tell you a ton about your ring and the module theory and the ideal theory. Yeah, so we want to know as much as we can about them. It's kind of a first step to understanding what the equivariant module theory is. All right. So now with the background out of the way, we can start looking at our two specific situations that we're going to talk about. So the first one is this example where we have the infinite variable polynomial ring with the infinite symmetric group acting. And the goal for this part of the talk is to classify the G primes. And since this is a specific ring with a specific group acting, we're going to be able to give a fairly explicit answer to this problem. And I should say that everything in this part of the talk is joint work with Rohit Nagpal. We're still writing the papers, but they should be coming out in the near future. All right, so first, the general strategy for classifying G primes. So it's not hard to see that if you have a G prime, then its radical is also a G prime. And here when I say radical, I mean its ordinary radical. It wouldn't really make sense to talk about the G radical because if you have a G prime, it's its own G radical. And so this means that we can consider this map from the set of G primes to the set of radical G primes given by taking radical. And so our strategy is to first classify the radical G primes and then analyze the fibers of this map. So in other words, figure out which G primes have a given radical. All right, so let's first talk about the first step, classifying radical G primes. So the reason that this is a tractable thing is that radical ideals are nice because we can reason about them geometrically. So we're going to define X to be the spectrum of our ring R. This is just the ordinary spectrum, not the equivariant one. And we're going to identify this with C infinity, just the set of all sequences of complex numbers. I guess this is really the max spec, but that distinction is not going to matter. So associating to an ideal A, its vanishing locus V of A gives you a bijection between ideals of R and closed subsets of X. There's a basic fact about how spectra work. And it's an easy exercise to see that this construction gives you a bijection between the radical G primes of R and the G irreducible closed subsets of X. And by G irreducible, I mean the set cannot be written as a union of two proper G-stable closed sets. Okay, and so this means that we can, instead of studying radical G primes, we can study G irreducible closed subsets of X, and that's nicer because we can picture them geometrically. All right, so there's essentially three things we can do to build G-stable closed sets. First of all, we can bound the number of distinct values in the sequence. Secondly, we can bound the multiplicity of the values. And third, we can impose algebraic relations between the values. So I'm going to do some examples now to illustrate each one of these points, and then we'll state the general construction and precise theorem. All right, so first of all, bounding the number of distinct values. So let Z be the subset of X that consists of all sequences that assume at most two distinct values. Okay, so for example, an element of Z will look something like just a tuple with a bunch of A's and B's, where A and B are two complex numbers. They can appear in whatever order. It could be as many A's and B's as you want, but there can't be any third value. And this set is Zariski closed. It's the vanishing locus of three variable discriminants. And it's easy to see that these discriminants vanish on Z, because if you pick three indices, two of them are going to have to be the same. So one of the factors in this product will vanish. And it's not hard to see that Z is exactly the vanishing locus of these things. All right, so good. We've built one interesting G-stable closed subset. So now let's look at another example. We're going to let Z prime be the subset of Z that consists of those two valued sequences, where one of the values occurs at most one time. So an element of Z prime will look something like a big tuple with A's and B's, where there's at most one B. And this is what I mean by bounding the multiplicities. A here, its multiplicity is infinite, unbounded, but we've bounded the multiplicity of B to be at most one. And this set, Z prime, is also Zariski closed. And it's cut out inside of Z by the equations xi minus xj times xk minus xl equals 0, where all the indices are distinct. And again, it's easy to see that these equations do in fact vanish on Z prime, because if you pick four distinct indices, only one of those coordinates can be B, and so in one of the factors, both of the things will be A, and so that factor will vanish. All right, and finally, the third kind of thing we can do is we can impose algebraic relations between the values. So let's fix some two-variable polynomial f, and we're going to define Z double prime to be the subset of Z prime, which consists of those sequences so that f of AB is equal to 0, where A is the value in the sequence that occurs infinitely often, and B is the value that occurs at most once. And this set is Zariski closed. It's cut out inside of Z prime by this equation. And let me explain why that holds. So imagine that the first two factors of this thing, xi minus xj times xi minus xk, don't vanish. We want to show that, I'm trying to show that these equations vanish. So if the first two factors vanish, then it vanishes. So assume that they don't vanish. So that means that xi and xj are distinct, and xi and xk are distinct. And therefore, xi has to be b, this value that occurs at most once. Because if it were a, then either xj or xk would also have to be a, and then this first factor would vanish. So if we assume the first factor doesn't vanish, we have isolated a and b. We know that xi is a, and all the other coordinates, xi is b, and all the other coordinates are a. So in particular, xj or xk, either one is a. And so this f thing here will give us fab, and that vanishes because that's the definition of Z prime. Z double prime is the locus where that vanishes. Okay? And notice that here we defined Z prime as a subset of Z prime, where this equation held. If we worked inside of Z instead of Z prime, we'd have to be a little more careful, because inside of Z we cannot distinguish A and B. Both values can occur infinitely often, so there's a symmetry between them. And basically all that means is that this polynomial f would have to be symmetric in the two variables, and you could then impose that relation. Okay, so hopefully that made sense. So here's the general construction. We're going to fix a tuple, lambda 1 up to lambda r, which is a non-increasing sequence where the lambdas are positive integers or infinity, and the first one has to be infinity. And we call this a partition of infinity. And we'll let x sub lambda be the set of all sequences where there are exactly r values in the sequence, and where the multiplicities of the values are given by lambda. So the first value, the value that occurs most occurs lambda 1 times, infinite. The value that occurs second most occurs lambda 2 times, so on and so forth. All right, so let's let H be the stabilizer of lambda inside the rth symmetric group. So we have a well-defined map from x lambda to CR mod H by taking a sequence in x lambda to the tuple of its values. So back in this example, we had a running example with the z's and the z primes and such. We had a's and b's. This map would take a tuple to the pair a comma b. And if we were working in z, then this H would be the full S2 symmetric group, and you can't distinguish A and B. So this map is well defined if you go to the quotient. Whereas in the other examples, when z prime, where we constrain the multiplicities, H would be trivial, and then you would actually go to C2 with no quotient because you can tell A and B apart. Okay, so we have this map. And if we have an irreducible closed subset W of this quotient variety, we're going to let x lambda of W be its inverse image back in x lambda. All right, so this is the general construction. And here is our theorem. This is the classification theorem for the radical G primes. We have a bijection between this data, choices of data, lambda comma W, and proper G irreducible closed subsets of X. Proper here just means it's not the whole space. And the way that the bijection works is you take lambda comma W to the closure of x lambda of W. So I should point out that x lambda and x lambda of W are not closed sets because I didn't bound the multiplicities. I said they had to be something exactly. So that means it's not going to be closed. And I phrase the theorem in this way just because it's a little easier to say. Describing the closure of x lambda in general, I mean, we know exactly what it is. It's just slightly annoying, and I didn't want to get into it. But yeah, we know exactly what the closures are, what appears in the closures, and the equations for the closures, all that stuff. And it's a fun exercise to try to do this in some small cases, like pick some small partition of infinity lambda and try to figure out what the equations are for x lambda or its closure. All right, so now that we understand the radical case, we want to go on to the general case. So recall that we are considering this map from G primes to radical G primes by taking radicals. And the previous theorem basically tells us what the target of this map is exactly. And we now want to understand the fibers. All right, so let Q be this ideal generated by the xi minus xj's. This is G stable. It's actually a prime ideal. So in particular, it's a radical G prime. And we have some argument using localization that reduces the study of arbitrary fibers of this map to the fiber at Q. It's just some statement about the local structure of these radical G primes kind of all resemble the local structure at Q. It's not a very hard argument or really that interesting, so I'm not really going to say any more about it because it's a bit notationally complicated. But anyway, the point is that we only have to think about what happens at Q, and that's very interesting, so we're going to talk about that. So we want to understand those G primes whose radical is this very simple G prime Q. All right, so anything that has radical Q is going to contain a power, some power of xi minus xj. So it's very natural to consider the ideal Qn, which is generated by the nth powers of the differences. Clearly, this ideal has radical Q for every n. So here's the main theorem on this fiber. So the ideal Qn is G prime if and only if n is odd. And moreover, these Qn with n odd are exactly the G primes that have radical Q. All right, so if you combine this theorem on the fibers of this map together with the previous theorem on the description of radical G primes and this localization argument, you get a full description of the G primes of this ring. Basically what happens for the fibers in general is that for each infinite part of lambda, you have to pick an odd number corresponding to the odd numbers here in these Qn's. We don't have a direct proof that the Qn's with n even are not G prime in general. This proof is kind of complicated, and the way it works is we show that there's some construction that gives all the G primes and it just spits out the Q sub odds, and so therefore the Q sub evens are not G prime. But it would be really nice to have a direct way to see that they're not G prime. The n equals 2 case is easy. For Q2, you can just do it by hand and show that Q2 is not G prime. And for other small values of n, you can do it on a computer. But we haven't succeeded in doing it in general. So as I said, this theorem is somewhat complicated to prove. There's a few different pieces to it, but I want to explain one key part of it. So this is going to be just an elementary thing, which is very important in the proof. So let A be this finite variable polynomial ring, and let little a be the ideal of this ring generated by the 2n minus first powers of the differences of the variables. And let B be the ring obtained by A just by adjoining one more variable t. And let little b be this ideal, generated by xi minus t to the n. Okay, so the key result is that the ideal A is the contraction of the ideal B. Okay, so it's clear that A is contained in the contraction from this equation. So let me explain what's going on here. So we look at xi minus xj to the 2n minus 1. We can write that as xi minus t minus xj minus t to the 2n minus 1. And then we can just binomial expand this power. And the point is that in every term here, one of those two exponents has to be at least n, and therefore it will belong to the ideal B. So that shows that all these 2n minus first powers belong to the ideal B, and since they're also in the ring A, they belong to the contraction. Okay, so that gives you this containment. But showing that you actually have equality, that A is actually the full contraction, is quite involved, or at least our proof is quite involved. It's a Grosvenor theoretic proof, and it's very long and very combinatorial. So if anyone has an idea about how to prove this more conceptually or has a cleaner way to do it, we would be very interested. Because it seems like a very simple and natural statement, and you might expect that it has a cleaner proof than the proof that we have. Okay, but anyway, that is the story of this situation. We have this complete description of the G primes of R. So a few more remarks before moving on. This is really just the tip of the iceberg of the results we have in this situation. We can do a lot more. So a few examples, we can actually describe the G spectrum of R as a topological space. So for instance, we know all the containments between the G primes. That's not obvious. It takes quite a bit of work. We also have a version of primary decomposition for G ideals. So we can write an arbitrary G ideal as an intersection of G primary ideals, having the normal uniqueness properties. And we also have some results on the structure of equivariant modules. Some of these results work in positive characteristic and some don't. It would be interesting to extend everything to positive characteristic, but we haven't thought too much about that yet. And finally, this ring R is kind of the simplest member of a family. You can consider the polynomial ring in variables xij, where the index I is bounded between 1 and R, and the index j is unbounded. So the ring that we were looking at was the little r equals 1 case. And this ring with general R has, it's still very nicely behaved in the equivariant setting. The relevant theorem, which maybe I should have said earlier, is that the ring is equivariantly Noetherian, meaning every ascending chain of G-ideals stabilizes. That's the theorem of Cohen. So we just did, everything I just said was for the little r equals 1 case, and it would be interesting to extend all this to general values of little r. And in some ongoing joint work with Rohit and Vignesh, we have figured out the case of radical G primes in this more general setting, but still don't know about general G primes. Okay, so now we're going to move on to the second topic, which is twisted commutative algebras. All right, so we're going to work over C, and recall that there's this notion of a polynomial representation of GLN or GL infinity. We're interested in GL infinity. And the definition I'll use is that it's just a representation that decomposes as a direct sum of Schur functors evaluated at the standard representation. So things like symmetric powers of the standard representation, or wedge powers of the standard representation, or other Schur functors. And a twisted commutative algebra, abbreviated TCA, is a C algebra equipped with an action of G, under which it forms a polynomial representation. I guess I should say it's a commutative, associative, unidal C algebra with this data. And the goal of this section is to understand the G primes in TCAs. So unlike the previous section, here we're working with kind of arbitrary rings. So it's not like we're going to be able to do an explicit classification. Instead, we want kind of a method to understand them, or some theoretical tools to describe them generally. So we're going to start by doing some examples, just to give examples of TCAs and G primes in them, so we have some idea of what we're working with, and that'll lead us to our main theorem. So first example, let's consider the ring A that is the symmetric algebra on CR tensor C infinity. So in other words, this is just the standard representation. C infinity is the standard representation, and this tensor product is just the r-fold direct sum of that with itself. So this is the polynomial ring in variables xij, where the I variable is bounded between 1 and r, and the j variable is unbounded. So this is an example of a TCA, and it's one of the simplest examples. So Stephen, Sam, and I figured out what the G primes in this case are, and they're exactly the G-stable prime ideals. So in other words, this case is kind of boring from the point of view of equivariant commutative algebra. You don't get any really interesting behavior. So this A is the kind of universal TCA with R copies of the standard representation, and so in other words, any TCA generated in degree 1 is going to be a quotient of one of these A's, and so the proposition holds for those two, and in fact it holds more generally for the so-called bounded TCAs. Bounded here means that you can bound the number of rows of the partitions occurring in A. So in this bounded case, we know exactly what's going on. All right, as soon as we leave the bounded case, we get interesting behavior. So here's kind of the key example, kind of the simplest example, which shows interesting behavior. Let A be the even subalgebra of the exterior algebra on the standard representation. So the exterior algebra is not commutative, but if we pass the even subalgebra, it's a commutative ring. It's a polynomial representation, so it is a TCA. Obviously, every positive degree element in this ring is nilpotent, because that's just how exterior algebras work. And so if you take the spectrum, the ordinary spectrum of this, it's just a single point. So there's no geometry really in this ring. However, the zero ideal is G prime. So in other words, you could say that this TCA is a G domain, despite everything being nilpotent. So that's pretty weird. Proof of this is pretty easy, so let's just go through it. So the graded pieces of A are these exterior powers, and those are irreducible representations of GL infinity. And so if you have a G ideal, it's a G sub-representation, and so it has to contain every graded piece that it meets. If it has anything in degree 3, it's going to have everything in degree 3, or I should say degree 4, because it's only in even degrees. So in other words, the non-zero G ideals of A are exactly the ideals you get by starting in some degree and taking everything larger than it. So I'm calling these the ARs here. And it's very easy to see that AR times AS is AR plus S. And so that shows that a product of two non-zero ideals is still a non-zero ideal. And that's exactly, sorry, the product of two non-zero G ideals is still a non-zero G ideal. And that's exactly what we need to check to prove that 0 is G prime. So that proves it. And from this, it's pretty easy to see that the G spectrum of A is exactly the 0 ideal and A1. I mean, A1 is obviously G prime because if you quotient by A1, you just get C, which is a domain. And it's easy to see that none of these other guys are G prime. So the G spectrum of this A just looks like the spectrum of a DVR, in other words. All right, one more example which shows even more interesting behavior. Let's take A to be the symmetric algebra on the representation sim2 C infinity. So you can think about this A as the polynomial ring in variables xij, where I and j are both unbounded, and I is less than or equal to j. So the decomposition of this ring as a representation is well understood. It's a kind of a classical fact. It decomposes as a direct sum of Schur functors S lambda, where the partition lambda is even, meaning that all of its parts are even. And the really important thing about this decomposition is that it's multiplicity free. So let's consider the ideal, I'm going to call it PR comma S, that's generated by the 2s plus 2 times r plus 1 rectangle. So what I mean by that is consider the Young diagram that is that rectangle, and take the corresponding partition, and then take that S lambda piece and take the ideal that makes. And it turns out that these guys are exactly the non-zero G primes in this situation. That is not at all obvious, but it's true. And furthermore, PRS is radical if and only if S is 0. So there are a ton of non-radical G primes here. I'll explain later on kind of conceptually why this is true. So in particular, we see that the G spectrum of this A as a set is just n squared, and n being the natural numbers, n times n, together with one extra point infinity, corresponding to the 0 ideal. And the topology on this is some kind of order topology. All right, so before we talk about general TCAs, we should try to understand this example 3 more conceptually. Because if we can't understand this example, we don't have any hope for more general things. And the best way to do this is through geometry. So spec A is the space of symmetric bilinear forms on C infinity. These radical G primes PR0, they're well known. They're just the determinantal ideals in this ring. They're in fact prime ideals. And the vanishing locus of PR0 is just the locus of forms of rank at most R. So the key insight which we extrapolated from that is that PRS should be related to the ranks of super bilinear forms. So that's suggested by, maybe I should say, this picture and some familiarity with super mathematics. And I should credit Steve and Sam here because he and I worked this out together in some joint discussions, and this was kind of the key insight to the general picture. Okay, so I assume many people listening to this talk may not be familiar with supermath, so let's go on a little interlude and describe just a bit of background there so I can explain what I need for what we're doing. So a super vector space is a Z mod 2 gridded vector space. So it's just a vector space that is given as a direct sum of two things, and I'm going to use this notation V0 plus V1 bracket 1, and the bracket 1 indicates that V1 is an odd degree. I think about V0 and V1 as just ordinary vector spaces, and so you have to put V1 in degree 1 to get the super vector space. And kind of standard notation is that C to the P bar Q is the super vector space whose even part is CP and whose odd part is CQ. So you can do everything you can normally do in linear algebra with super vector spaces. You have linear maps and kernels and cokernels, so on. It's an abelian category. You can also form tensor products of them, and this is done just in the usual way, how you tensor graded things. And the thing that's interesting about supervector spaces is that, well, in the language of category theory, we have this monoidal category, and it has a symmetric structure. There's an isomorphism between V tensor W and W tensor V. You have the standard one, but in the super setting, you can make a more interesting one. And that's entirely responsible for all the interesting features of supermath. And the way that this interesting symmetry works is that you send X tensor Y to negative Y tensor X if X and Y are both odd. So when you commute two odd things, you throw in a sign. And otherwise, you just commute them like normal. And so essentially you have supervector spaces, which is this symmetric tensor category, and you can carry out kind of most of algebra inside of it. You can define supergroups and super schemes and so on and so forth. So for us, it's going to be important to understand symmetric bilinear forms on supervector spaces. So the definition is that it should just be a map from a linear map, or a map of supervector spaces from sim2v to C. And so let's look at this more closely. So remember, V is decomposed as V0 plus V1 in degree 1. And so sim2v, you can expand it using the usual binomial theorem for sim2. You're going to get one piece that's sim2v0, one piece that's sim2v1, 1, and then the cross term, which is v0 tensor v1 placed in degree 1. And this cross term has to map to 0 under omega, because this C that we're mapping to is concentrated in degree 0, and this cross term is concentrated in degree 1. So it just has to map to 0. And now here's kind of the interesting thing. The way that this sign rule works, the symmetry of the tensor product, means that sim2 of v1, 1 is actually wedge 2 of v1. So the sign rules make sim change into wedge. And so what this means is that this omega really corresponds to a pair of omega 0, omega 1, where omega 1 is just an ordinary symmetric bilinear form on the even part of V, and omega 1 is an alternating bilinear form on the odd part. Okay, so this is how you understand symmetric bilinear forms on supervector spaces. All right, so let's go back to our TCAA, the sim2 example. So if we look at A of C infinity infinity, this is a superalgebra. So I should clarify here. If we have a TCA, it decomposes into Schur functors. That's just definition. And well, Schur functors evaluated on the standard representation of GL infinity. It turns out that polynomial representations of GL infinity are equivalent to the category of polynomial functors, just by associating to the polynomial functor S lambda the representation S lambda of C infinity. So a TCA, instead of thinking about it as a representation of GL infinity, we can think of it as a polynomial functor. And then you can always plug in supervector spaces into polynomial functors. So we can take our A and just plug in the supervector space C infinity infinity. And what that gives you is sim2 of C infinity infinity. Okay, so that's a commutative superalgebra, and we can therefore take its spectrum, and that will give us a super scheme. And that's the space of symmetric bilinear forms on this vector space C infinity infinity. Now, if you haven't thought about super schemes before, they're really actually not that hard to think about. They always have a reduced subscheme, which is an ordinary scheme. So there's an underlying topological space, which is just the topological space of an ordinary scheme. And basically, super schemes are just schemes with some extra nilpotent stuff. And in this particular case, the underlying reduced scheme is just spec of our A times spec of B, where B is sim of wedge 2 C infinity. This corresponds to this omega 0, omega 1 parameterization. So it turns out that this V PRS guy is exactly the locus of forms omega where omega 0 has rank at most R and omega 1 has rank at most 2S. So this super math point of view gives us a very nice geometric way of seeing these ideals. And this suggested what might be true and what I ended up proving is true in general. So suppose that we have a TCA A and we have two G ideals A and B. then A and B have the same G radical if and only if they have the same vanishing locus when you go to C infinity infinity. And also, the G radical of A is G prime if and only if this locus is irreducible. Okay, and you can compare this to a familiar statement, which is that A and B have the same radical if and only if they're the same vanishing locus, and the radical is prime if and only if the vanishing locus is irreducible. So basically, you can just throw G's into these statements as long as you go to the superspaces. And so the upshot of this is that if you use A, C infinity infinity, you use the superspaces, the geometry there is rich enough to see the entire G spectrum. And that's not true if you don't go to superspaces, because we had these examples where there were interesting G primes but no geometry. Okay, so this theorem and some related results give you effective tools for analyzing G primes in the TCA case. And just a few further remarks in this direction. So if you combine this theorem I proved with the theorem that Drysma proved, you can show that if you have a finitely generated TCA, then its G spectrum is a Noetherian topological space. It's unknown and an important problem right now if finitely generated TCAs are Noetherian, but theorems like this are evidence that it might be true. This theorem I proved is reminiscent of a theorem of Deligne, which says that certain natural tensor categories emit a fiber functor to supervector spaces. So that's another situation where you have an interesting class of things that you care about that aren't obviously related to supervector spaces, but turn out to be. And so it'd be interesting if there were any connection between my theorem and Deligne's theorem. And finally, all this breaks horribly in positive characteristic, and it would be interesting if you could figure out how to generalize it there. Okay, so that is the talk. Thank you for listening.